All right, welcome to this explainer. Let's just kick things off by imagining a total nightmare scenario. Picture this. You've got your personal bank account open in one tab, or maybe your private university grades. Then, in another tab, you accidentally click a link to some random sketchy website. Well, what's actually stopping that sketchy website from just magically reaching over into your bank tab, reading all your financial data, and shipping it off to a hacker? The answer is this invisible shield built right into the very core of the web. Today, we're diving deep into our expert source material to demystify that exact shield. It's called the Same Origin Policy.
Here's a quick look at the agenda our subject matter experts have laid out for us. First, the web's golden rule. Then, the anatomy of an origin, followed by when the policy fails, secure cross-origin communication, and finally, the automatic exceptions.
So let's jump right into Section 1, the web's golden rule.
Our source material really hits the nail on the head when defining the fundamental security model of the web. It says, if you remember one thing from this class, this is it. 2 pages from different sources should not be allowed to interfere with each other. It sounds incredibly simple, right? But honestly, enforcing this across the chaotic, wildly interconnected landscape of the entire internet, that is a massive engineering feat. Because think about it, if Site A could just seamlessly read the data of Site B, the entire concept of online privacy would just collapse instantly.
To really wrap our heads around this, the experts use this brilliant comparison. They compare your web browser to an operating system. So on your computer's OS, like Windows or Mac OS, you have a kernel, and that kernel strictly isolates different running programs. Your calculator app can't just randomly peek into your password manager's memory. Well, the web browser acts exactly like that OS kernel, and an origin on the web is perfectly analogous to an isolated OS process. Sites rely entirely on your browser to enforce these boundaries, meaning if there's a bug in the browser itself, all these rules just go right out the window.
Moving right along to Section 2, Anatomy of an Origin. Defining exactly what an origin actually is reveals precisely where the browser draws its hard security boundaries. You see, an origin isn't just the domain name. According to the source material, it's a strict combination, a tuple, of 3 distinct elements: the protocol, the host name, and the port number. So looking at this URL, the protocol is HTTPS, the host name is example.com, and the port is 4000. All 3 of these have to match exactly for 2 pages to be considered from the same origin. The path, the query string at the end, the browser actually doesn't care about those for this specific security check. It is all about protocol, host, and port matching perfectly.
Let's do a quick rapid-fire check to see this in action. Notice how even the tiniest tweak completely breaks the same origin role. Let's say our base URL is https example.com. If we try to access example.com/b, we're good. Yes, that's the same origin because the protocol, host, and default port are identical. But what if we add www to the hostname? Boom. No, hostname mismatch. What if we drop the S and swap HTTPS for HTTP? No, protocol mismatch. And what if we try to access port 81 instead of the default? Absolutely not. It is an incredibly strict rule, and for very good reason.
But what happens when that strictness gets in the way? Let's hit Section 3, when the policy fails.
So, this incredibly strict rule actually creates a massive headache when 2 legitimate sites legitimately need to talk to each other. For example, let's say Stanford University has login.stanford.edu and access.stanford.edu. They're different subdomains, so by our rules, they are different origins. They literally cannot communicate. Historically, developers use this workaround called document.domain to force 2 subdomains to be treated as the same origin. Both cooperating sites would just execute document.domain equals stanford.edu. This basically tells the browser, hey, just treat us both as the top-level stanford.edu. It solves the communication problem beautifully, but man, it opens a very dangerous door.
Because as our subject matter experts point out, if you broaden your policy to a top-level domain, any subdomain can suddenly join the party. Enter the attacker domain. If a malicious user manages to get control of attacker.stanford.edu, say maybe an old, forgotten student server, they can also run that exact same line of code to opt in. And suddenly, this red attacker domain is considered the same origin as the highly secure login and portal pages. They can completely bypass the shield and snatch your private data.
Thankfully, there's a better way. Let's look at Section 4, Secure Cross-Origin Communication.
To fix vulnerabilities exactly like the one we just saw, expert web architects introduced the Post-Message API. Let's watch this highly secure but delicate turf war play out visually. Starting with our secure blue access portal, it needs to securely know the name of the user who's currently logging in so it can display their specific data.
Because of the same origin policy, it can't handle the login directly if the login is hosted on a different subdomain. So the blue portal securely embeds the green login window as an iframe. This allows the user to safely type their credentials into the actual login.stanford.edu page. Once the user logs in, the green login window successfully authenticates them. It then uses that post message API to pass a data object, like the username Pharos, back up to the blue parent window. But here is where it gets incredibly tricky. Doing this without strict validation is just a complete disaster waiting to happen. Because what if the sender doesn't specify who they're sending the message to? If an attacker embeds that exact same green login box on their own malicious red site and the user logs in, well, the green box just blindly broadcasts the username to whatever parent window embedded it. The attacker easily intercepts the message and steals the identity. This shows exactly why the sender absolutely must validate its destination. Now let's look at the receiver. If the blue access portal is just blindly listening for any message that says here is the logged in user, our red attacker can easily embed the blue portal in an iframe and spoof a totally fake login message. The attacker sends a message saying, hey, the logged in user is Mark. If the blue portal doesn't validate where the message actually came from, it gets completely tricked. So the subject matter experts give us the absolute golden rules for using post-message securely. They are twofold, and you have to get both of them right. Step 1. The sender must strictly specify the intended recipient's origin. The browser will actually enforce this and drop the message if the parent's URL has changed. Step 2. The recipient must strictly validate the identity of the sender to ensure they aren't being fed spoof data by a malicious iframe. Always specify the destination and always verify the source. And now for the ultimate plot twist in web architecture. Section 5, the automatic exceptions. After establishing all of these intense, unbreakable rules for data security, it turns out the same origin policy has massive automatic exceptions built right in. While a script can't magically read raw data from another origin, your browser will happily load resources from absolutely anywhere without a second thought. Images? Yeah, you can hotlink a meme from another site entirely. Scripts? Think about how Facebook like buttons, Google ads, and tracking scripts are embedded on millions of websites. Style sheets? We load fonts from external Google servers all the time. The browser just automatically allows these static resources to execute and render, completely bypassing the strict origin isolation we just spent all this time learning about. Which leaves us with a truly provocative question about the foundational quirks of the internet that our source material ultimately asks. Why on earth was the web designed this way? I mean, why build an impenetrable vault for data, but leave the windows completely wide open for external images and third-party tracking scripts? It's a paradox that has fueled countless security vulnerabilities over the decades. So as you browse the web today, ask yourself, how many different origins are silently loading their scripts onto the page you're reading right now, all perfectly allowed by the very rules